Hello and welcome back to Calculus 3. This is the last section of chapter 11 on curvature and normal vectors. This is one of the sections in Calc 3 where the problems will be really good for killing time and developing carpal tunnel if you already don't have one, meaning long calculations, right? We'll start with curvature. The easiest way to understand curvature is to just simply say that it's going to be quantification on how much the line turns, how quickly it bends. So that's just, street talk to understand what curvature is. So you will say curvature is 1, curvature is 7, curvature is 0.1. Straight line, curvature is 0, because straight line does not curve at all. So if you want to quantify curvature, it makes sense to say that straight line has curvature 0. So what is curvature? Curvature is simply going to quantify the amount of bend that line makes as you look at the line. So your curves, the turns as you drive the car, right? The curves that curve more have a higher number, and those that are really mild have a lower number. We are going to define curvature, and then we're going to put a theorem to see how to calculate curvature. So we start with the definition for curvature. Let R describe a smooth parametricized curve. If S denotes the arc length, and T hat equaling R prime over magnitude R prime is the unit tangent vector, the curvature K expressed through arc length is K of S is equal to dt hat over ds, the magnitude of it. This is definition, and we are not going to calculate using this definition. So if you have some curve which is described through the vector R, and you have your unit tangent vector because the motion, let's say, is this way, curvature Ks is the amount of how quickly it bends. See, your arc length is a short path, and on that path, I drew this badly because the tangent vector and R vector always need to be perpendicular to itself, so I have to fix R. There we go. So This is, guys, the change in the tangent vector. But remember, this is a unit vector, so you can only change the direction, right? Are we all agreeing on that? Unit vector has its magnitude fixed to be 1. And the only thing that you are allowed to change for a unit vector is its direction. Now, knowing that arc length is the path on which the tangent vector is moving along that path, and we know that derivative measures the change, and since it's a tangent vector, the only thing we can change on the tangent vector is not its length, but its direction. Since you're measuring the change over there for a curve that is, let's say, lazy, so there is not much curvature there, this vector will slowly change its direction as it's progressing on the line, because it takes a long time, right? It's a long way to go in the same time along ds, along the curve, and as you can see, the angle is changing slowly for d theta, for the tangent vector, which is this puppy here. If you have much quicker bend, it's going to change that much faster. You see that? So, when you're defining the curvature, you simply say curvature is going to measure how fast the tangent vector is changing its direction. And that's only definition. We are not going to calculate this way because we do not have our functions in 3D given through arc length parameter. If you want to use this formula, you will have to take your parametric equations and somehow put them into the S, the arc length parameterization, and then you will have to go from there. So instead of us worrying about that conversion, it's much better and easier to convert this formula once and for all into the formula that will include dt, because our parametric equations are given as dt. So now we are going to have a theorem which will tell us which way we are going to calculate the curvature. So let's say in blue is the theorem, and I'm going to write the formula k of t, right, because it's a curvature, but now it's in respect to parameter t, is given as magnitude of t hat prime as a function of t divided by the magnitude of r prime of t magnitude. This is the formula that you are going to use to calculate stuff. I'll put here honors. This is derivation that you are responsible for, and it will show up few times in during Calc 3. Papa? Yeah, so honors, it's the switch from one to another. So your KS formula, which was dt over ds, will be multiplied by 1 over dt, 1 over dt. To give you dt hat over dt divided by ds over dt, and I'll put here as a side note, ds dt is velocity v because it is distance over time. Arc length is a distance, right, that you cover. So distance divided by time is velocity. Therefore, your formula up there becomes 1 over v dt over dt. And now we know also, as the second asterisk over here, that our v is actually r prime. So you get derivative of t divided by derivative of r. And that's how you obtain. So this is the proof which converts the red formula from definition into the blue formula that we use for calculation. So if you are in honors, you are responsible for this black derivation here. If I ask, convert. Everyone in a class has to memorize the blue formula or you are doomed. That's the only way you compute the curvature. So let's do the problem. Compute curvature of the unit circle. This could be a standard exam problem. As you can see, you are expected to know parameterization for a circle, which is your R. And then you're expected to know formula for curvature and then compute the whole thing. So let's do this together now. What is the parameterization for unit circle? What are the parametric equations for unit circle? Those are polar ones. Well, actually, we can use, yeah. So what is the R? You said what? R cosine t, and R sine t. So this is circle in general, because this is for any R, right? Any radius. Now, what's the unit circle? The one that we need. What's the radius in the unit circle? Thank you. Almost had a heart attack over there. Please say something. So R is equal to 1. So we have cosine t sine t. Great. Now you have your unit circle parametric equations. Next question is, what is the tangent vector, unit tangent vector? How do we calculate that one? Unit tangent vector. R prime over magnitude R prime, yes. So unit tangent vector, which we need, is R prime over magnitude R prime. Perfect. So we need R prime. Okay, well, we'll do that. What's the derivative of cosine? Very good. And what's the derivative of sine? Cosine. Now, what's magnitude of R?
Isn't it going to be sine squared, negative sine t squared plus cosine t squared?
Perfect. Under the
square root.
Yes. Negative sine squared plus cosine t squared under the root, so it's 1. Making our tangent vector to be negative sine t cosine t divided by 1, just negative sine t cosine t. Great. What was the formula for curvature? What is the formula? We just did it. Magnitude of t hat prime divided by of r prime. Thank you. Oh, hold on. We don't have the t prime yet, right? We just have t. So t prime is negative cosine t negative sine t. And now curvature of t is magnitude of t. That's going to be again the square root with sine squared, cosine squared. It's all 1. R prime will say it's 1. And the answer is 1. What's the curvature of the unit circle? It's 1. Does this say that the curvature of the unit circle is 1? That is the curvature of every circle 1? Is the curvature of every circle 1? No. Curvature of every circle. Since I don't have ice and ice skates, I'll use this instead. Circle, 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 circle. Huh? This one is going to curve much less than that one. Now ice skating, pull the hands in, pull the hands out, and with a spin. Yeah. So this circle has smaller curvature than that circle. That's a smaller circle right there. Because it's faster turning over here. You start spinning over here, this spins faster. It's a bigger velocity here and there. Because velocity, linear velocity depends on how far you are from the center. The closer you are to the center, the faster you spin. Are these things important? Hell yes. What does that mean for your Blu-ray discs? When it's reading over here and when it's reading over here. That type of engineering has to be calculated in, otherwise you're never going to be reading stuff properly. Right? So, you have to calculate every time. Now, those of you that are vicious and want to learn this the proper way, you are going to redo this problem by not using the unit circle. You are going to use capital R and redo this problem for every radius that you can encounter to get this to be in terms of capital R. And then you will have the mathematical model for calculating curvature of any circle that depends. That depends on a radius. This is how you develop formulas in physics and engineering. Through mathematics. You calculate example for radius 1, calculate example for radius maybe 2 and 3 to get your feet wet and see how the calculations work. And then you immediately put capital R instead of the radius 1, 2, 3. And you run the same calculation, but now you get to drag that R through your algebra. Your answer will be in terms of R. So now if I'm designing something, I have the formula that I can program in. And the formula says, and the answer, 1 over R. So now I know, right, that if the radius is 6, curvature is 1 over 6. If the radius is 13, curvature is 1 over 13, and so on. So you develop the master formula for any radius that anyone can throw at you, and that's the formula that you use if you are programming your DVD, firmware, and other stuff that has spinning as a part of it. Good. We already said that the curvature of the straight line is 0. Well, if you think about it, R is going to be linear because you are talking about the curvature. R prime that gives you your t is going to be constant because the one before was linear. And finally, t prime is going to be 0 because this guy was constant. So if t prime is 0 and you're dividing it by r prime, there's your 0 for curvature of the line. Does that make sense? So you will have a linear line on R because you're looking at a straight line. R prime, because this was linear, is going to be constant. And then finally, R prime gives you t. T prime is 0 because this one was constant. Done deal. So you can run that argument verbally. You don't even have to compute it. But obviously, you should compute that to prove that. So here, this is examples for you. Number 1, compute K for any R circle. And number 2, prove K equals 0 for straight line. So these are the 2 problems that you can do at home and practice these skills. Parametricize first to get your x and a y, or z if you want to, and then run your calculation. I hope you see that this equation is also dimension free. You can do this in any dimension because it's utilizing the entire vector. So if you have 2 dimensions in your vector, it's a 2D problem. If you have 15 dimensions in your vector R, it's a 15-dimensional problem. There is no mathematics over there that will limit your dimensions, like in a cross product, right? As soon as you see cross product, you are limited to dimension 3 or dimension 7 or dimension 11, so only certain dimensions are allowed to have cross product. If you don't have cross product laying around in equations that have vectors, that equation is valid in any dimension. So can you talk about curvature of a sphere? Yes. Next time some idiot tells you that the Earth is flat, calculate the curvature of the Earth. Google the radius, right? And you can say here, curvature of the Earth is given by this. So this is going to be 1 over radius. You figure it out, which is why they can't see that it's curved, because it's going to be a very small number, 1 divided by the radius of the Earth. And radius of the Earth is a large number in miles. So maybe you even can change that into inches if you'll learn some more. Anyway, so that's curvature. Very simply, curvature calculates how fast the line bends. Now we move on to principal normal vector. Oh, there's the alternate curvature formula. I don't like it because it has cross product. I just talked about the limitation of a cross product. What is the limitation of a cross product? 3 dimensions. Can I do the circle with this formula? No. This is why I don't care about this formula. I have a formula that calculates everything in any dimension. If I want to talk about 11-dimensional space, I talk about 11-dimensional space with the original K of T formula. This one bounds you to 3 dimensions. Now, guys, you might see this formula in your physics class, depending on how vicious your physics class is. In kinematics, for the object that is on the surface, that is curved, and in that case, you're certainly going to run into this formula if you're learning higher levels of gravitational field, because three-dimensional space, right? Three-dimensional space. So that portion of physics doesn't have to worry about being free in as many dimensions as you want, and definitely doesn't have to worry about circles. So, because again, planet is a sphere. All right. So, yeah, perfectly fine. Your v is velocity, which is your r prime, and your a is your acceleration, which is r double prime. So you can recast that formula into r primes and r double primes, and then go from there if you want to understand the three-dimensional version of the formula. As I said, it's restrictive, so I don't care about it, but you definitely should look into it and have that possibility, right, in your head worked out as well. Principal unit normal vector. All right, before we start this section, let's all grab our wrists for the hand that we are using to write and work it out, work it out. We do not want carpal tunnel, right? This is something that we all need to do because each one of these problems is going to be 17 pages long, right? There we go. Now that we're all set and ready, we're going to do definition, and then we'll have the time to do an example. So also for homework, right? We go like this before exam. This is the last problem that you are going to do on your test, because if you get hang up on this problem as a first problem, the rest of the test is not going to go well. Principal unit normal vector. We know what the normal vector is. Normal vector is 90 degrees to the tangent vector. So r prime, tangent, tangent prime, and then we go finally into normal vector. Do we see the series of derivatives, which is vectors with 3 components each? Of course, each problem is going to take an hour. So let's go. Definition, then the theorem. Same conversion as before. So definition. Let R describe a smooth curve parametricized by arc length, and that arc length is ds. The principal unit normal vector at point P, the principal unit normal vector at point P on the curve with curvature different than 0. This qualifies straight lines, right? Is n hat of s dt ds divided by dt ds magnitude, right? It's a unit vector, which is technically 1 over k dt ds. These t's are all unit vectors, so they all have hats. Now, this is not the user-friendly formula, so we convert this in our theorem, saying that the normal vector in respect to parameter t, which is what we want to use to compute, is going to be dt dt divided by dt dt magnitude, which is simply t hat prime over the magnitude of t hat prime. This is the formula we want. I'll write the note over here. The dot product between these two is 0. And that should be common sense because they're perpendicular to each other. It's called a normal vector. It's normal. That means 90 degrees to the tangent vector. Well, if there is 90 degrees between two vectors, their dot product is 0. So that might come in handy as you go through stuff. I'm going to jump into homework. And I have to solve a quiz now, so I can flip to homework. All right, there we go. And we are going to go with the formula now to do the principal normal vector. And let's pick any of these problems here. I'll let you pick the problem. 27 through 34. Where trig, we have polynomials, more trig. There is ln cosine t. That one? No. 33. With a t squared and a t. You pick the worst possible. I was hoping someone is gonna say ln of cosine t, because that is the easiest problem of all. But since you picked 33, in your infinite wisdom, let's do it. $33 from homework. T squared and t. We're asking about the normal vector. We know that our target is t prime over t prime magnitude. R prime, t prime, assemble the formula and you're done. Does it make sense? R prime gives you t prime, and then the formula. All right, so we have R prime is 2t and 1. Easy, right? And now we assemble unit vector t as r divided by r prime divided by r prime magnitude. This is where the stuff goes to hell, right here. You have your r prime, so nice and sweet, and then you have its magnitude as a square root of 4t squared plus 1. Great, we have a tangent vector.
I was saying, can we also just distribute the square root of 4t squared plus 1 on both sides?
Yes, that's the next step. Very good. So now it's 2t over square root of 4t squared plus 1, comma 1 over square root of 4t squared plus 1. Beautiful.
And then can we also have distributed it to the top as well? Will we simplify it?
No, that's it. There's nothing else you can do. Split it. All right. Are we ready for t prime? You gotta take these derivatives now. Each one of these, you have wonderful quotient rules with the chain rules embedded. So let's flip our notebook sideways so we can fit everything. I can generate infinite paper to the right, so we're good. Right? T prime. And we have the quotient rule. Square the bottom. Then write 4t squared plus 1 times derivative of the top minus copy the top times derivative of the bottom, which is 1/2 4t squared plus 1 to the negative 1/2 times the 8t derivative of the inside. Beautiful. That's the first component. And now we have to do the derivative for the second one. Now, second one is much easier because you can just write this as 4t squared plus 1 to the negative 1/2. So that derivative is much easier as negative 1/2 4t squared plus 1 to the negative 3/2 times the derivative of the inside, which is 8t. It's 1 over. I just brought this as a negative 1/2 exponent. Oh, there's something else? Alright. I told you, just spin the hat normal and it'll be fine. Now we need to plow through this algebra. It's his fault. You all know that, right? Someone did ask for that ln problem, which would make it a joke, but what can we kill over here? We can kill these 2's, yeah. Alright, so we have 2 square roots of 4t squared plus 1 minus 8t squared over square root of 4t squared plus 1 divided by 4t squared plus 1, comma, negative 4t over 4t squared plus 1 to the 3/2. Now, for the first component, we are multiply the square root 4t squared plus 1 and square root 4t squared plus 1 to get rid of the double fraction square root part. So we have t hat square root times square root is just 2 times 4t squared plus 1 minus 8t squared. The square roots just cancel. And on the bottom you have 4t squared plus 1 to the 3 halves. Because you had 1 and then plus 1 half is 3 halves. Which is great because it matches the second term. Now, t prime is 8t squared plus 2 minus 8t squared. Those die. Over 4t squared plus 1 to the 3 halves, comma negative 4t over 4t squared plus 1 to the 3 halves. Finally, t hat is 2 over 4t squared plus 1 3 halves and negative 4t over 4t squared plus 1 3 halves. This is your t prime. To calculate your normal vector, you have to find the magnitude of this and then divide into t prime. So now we are looking for magnitude of that. Yes?
Just one question. How did you end up, well, you said it became 8t squared. I see why the 2 and the 4t squared, but why is it minus 8t squared?
This one?
Yeah, I missed the part. How's that?
Okay, let's take a look. So, when you are at this step, this red square root will distribute to both terms. In the first term, square root times itself just loses the square root. In a second term, they cancel, and you just have 8.
But up there in the top, it says 8t, and then it goes to 8t squared over the square root of.
Yeah, because it was negative 1/2. Negative 1/2 is the division.
Yeah, okay.
Bueno?
Yeah, good.
Which is the reason. So this negative 1/2 created this negative, this square root in denominator, which warranted multiplication by the square root to kill it. We don't want double fraction.
Yeah, okay.
Now, you have to simplify all of this as much as possible because your original formula for normal vector is calling for division by the magnitude of the tangent vector. You do not want to look for the magnitude of the tangent vector here.
Yeah.
Right? So you have to grind through algebra to calculate the easiest possible form so that you can eventually calculate the formula. So now that we finally have our simplified version of t prime, we can square each of these and add them up under a square root to give you the denominator of the normal vector. So t hat prime magnitude is the square root of 2 over 4t squared plus 1 to the 3 halves squared plus negative 4t over 4t squared plus 1 3 halves squared. That gives us, now the cool part here is that you get 4 over and then it just kills the half. So you have 4t squared plus 1 cubed plus 16t squared over 4 t squared plus 1 cubed which gives you 16 squared plus 4 over 4t squared plus 1 cubed square root, which is this nice square root of 16t squared plus 4 divided by 4t squared plus 1 to the 3/2. So there's your magnitude. Yes.
Shouldn't there be a 1 with the magnitude t instead of that prime?
These are primes. Thank you. We're almost there. We are now going to put the normal vector together for the first time. Normal vector is a unit vector. You are taking your t prime, which was here. So that's vector 2 divided by 4t squared plus 1 3/2 comma negative 4t over 4t squared plus 1 3/2, and we are dividing that by the square root of 16t squared plus 4 over 4t squared plus 1 to the 3/2. Now the amazing thing is that if you multiply, the denominators are the same. If you multiply top by 4t squared plus 1 3/2 and 4t squared plus 1 3/2 in denominator, they all just cancel, leaving the normal vector as 2 over square root of 16t squared plus 4 comma negative 4t over square root of 16t squared plus 4, and that is the answer. So next time someone tells you, what do you know? Do this calculation for them. Ask them if they can spell unit, principal unit normal vector after all of this. Right? What was the problem that gave us this calculation? There you go. You have what, the 2 pages over there? How are you doing on this, right? So the exercises are this, like that. Then you can do a little bit of this as well. It's not as important, right? But this is, other good ones are this and that, right? It all works out, and you're not going to have problems with your wrists as you. This is what gamers do for before long gaming sessions of 12 hours, so they can make more money than whatever. Yes.
So,
yes, this is our unit normal vector, and I said make sure you do this last. Because if you are stuck with this at the beginning of the exam with 9 problems to do and you already burned 40 minutes, the panic and anxiety are going to start rolling up, and you're going to get paralyzed at the exam rate plus wisdom. So, test taking skills to open the exam, you find where this problem is, and you leave it last. Now I am going to use trig and lns, so it's not this long. Obviously, right, it still looks like you go for t squared t because that looks nice, and that should give you a nice, right? I know that if you have ln, you go, because the derivative of ln takes the function, just right? So that ln dies in the first one, leaving the trig behind. And leave the trig behind, 9 squared plus 1 sine squared, every time is 1. You always want to see ln's and trig in these problems. And you want to stay as far as possible from any polynomial, as you can see. Like if you can pop a dimension, right, or go into parallel universe away from polynomials, do that. Because as you can see, this sparked all of this. Right? And it starts beautiful with this derivative of 2t and 1, right? This was the line when you thought you're winning, because that's much easier than this. But as soon as this one kicked in over here, and you said, oh, I need the derivative of that, right?
Yeah.
You feel, yeah. So any other polynomial question will do much worse than this, clearly, right? Because as soon as you go up in powers, you go up in powers over here, which translates into higher powers down there. So you definitely want trig, because that always simplifies, and you definitely want ln's. They're great. I haven't seen this problem with these ever. No one ever posed. Maybe I should make up one and see what happens. Deal. There's one more part of this lecture at the end, which applies this to normal and perpendicular vectors for components of acceleration vector. That's highly applied physics for kinematics of motion, so I won't bother you with that. There are formulas that you can use to do these things. But you have already a lot of formulas to worry about in that, so since this is so specific, clearly if you are a physics buff, you should look into that, and we can discuss that. Just stop by my office hours and I'll show you everything that you need to know. This calculation will end the lesson on normal vector. And in chapter 12, we get to use normal vector, which means normal vector becomes a little side calculation. It's called academic inflation, right? Someone got a PhD over this stuff. Now you do it as a homework problem. It's like it's one of your problems on the test, right? Or someone was slaving a year to figure it out and define it, right? So that's that, and let's talk about some other stuff. So bye.